Hello, YouTube. I'm Dr. Paul Kerstetter, and today I want to talk about crossing clock domains in FPGAs. When all the rules are followed, flip-flops behave very predictably. But when data moves from one clock domain to another, flip-flops can act unpredictably. Fortunately, there are techniques to handle this issue. They aren't perfect, but they work quite well. Now, if your design happens to have a bad clock domain crossing, the question is, will Vivado alert you? The answer is yes. I'll show you exactly where to find the warning early in the design process. But first, let's discuss why flip-flops can behave unpredictably in the first place. Crossing clock domains in FPGAs. How to tell in Vivado if there's a bad clock domain crossing. For flip-flops to behave predictably, the design must follow certain rules. Specifically, the data must not transition too close to the clock edge. How close is too close is determined by the setup and hold requirements of the flip-flop, which define a critical window around the clock edge. To ensure safe operation, data is typically synchronized to the clock so that it never transitions within this window. But what happens if we break the rules? In the diagram, the data is transitioning within the window around the clock edge. This can occur if the data is independent of the clock, in other words, if it is an asynchronous signal. Because the data transition occurs so close to the clock edge, the flip-flop cannot determine whether the data is a 0 or a 1, and may output a voltage somewhere between the logic 0 and logic 1 levels. This is known as metastability, and it can cause serious problems in a digital system. Rather than transitioning smoothly from 0 to 1, the output of a flip-flop can linger for a while in an intermediate state before eventually settling to either 0 or 1. However, the probability that the flip-flop remains in this unknown state decreases over time. Actually, it decreases exponentially. For a great read on metastability, check out High-Speed Digital Design, a handbook of black magic by Howard Johnson and Martin Graham. One common solution is to use a synchronizer, which typically consists of a pair of flip-flops connected in series. The way it works is fairly straightforward. If the first flip-flop experiences a metastable event, the extra time before the second flip-flop clocks the data in allows the signal to settle to a stable logic level. In other words, the first flip-flop absorbs the uncertainty, and by the time the data reaches the second flip-flop, it is much more likely to be a clean 0 or 1. This simple technique significantly reduces the risk of metastability propagating through your digital system, though it cannot completely eliminate it. The key idea is that adding a second flip-flop provides the system with a buffer time for the signal to resolve itself. The synchronizer can be used to cross from one clock domain to another. Another solution to the clock domain crossing or CDC issue is to use a FIFO or first in, first out buffer. A FIFO is a type of memory structure that allows data to be written in one order and read in the same order like a queue. When used in CDC scenarios, the FIFO acts as a buffer between two clock domains, allowing data to safely transfer from one clock domain to another, even if the two clocks run at different frequencies or are asynchronous. Compared to a simple flip-flop synchronizer, a FIFO is particularly useful for high throughput or bursty data transfers, where multiple bits or words need to cross clock domains reliably. It also provides flow control, ensures that the destination domain can process data at its own pace without overflowing or underflowing the buffer. In short, using a FIFO for CDC is a robust method for safe, efficient, and high bandwidth data transfer between asynchronous clock domains. Now that we've covered the challenges of crossing asynchronous clock domains, let's move on to the Vivado demonstration. In this demo, I'll show you how Vivado can detect and warn you about a problematic clock domain crossing. Okay, this is the top level VHDL code for our Vivado demonstration. Let me just briefly describe what's in the code. This is the unsafe version of a data crossing clock domains. And as you can see in our top level port in our entity, we have two clocks, clock A, clock B. We have a signal, which is a data in A signal and a data out B signal. Both of those signals are 8 bits each. We have one process here, the clock domain A process, which takes data in A and outputs it to data cross, and that's clocked in by clock A. So this is the clock domain B process, which is clocked. You can see it's clocked by clock B, and data cross is fed into the flip-flop, and is the output is data out B, which is our output. So there's two clock domains, and there's two processes, and there's one process per clock domain, and we have data going in one set of flip-flops, coming out at those flip-flops, and then going into the second set of flip-flops, which is clocked by a different clock, and then going to the output. So this is an unsafe crossing of data through two clock domains. So let's minimize that window, and let's go ahead and look at the test bench. So in the sources window, the test bench can be accessed. Let's go ahead and expand the window. And once again, we have two clocks, clock A, clock B. And then we have two signals, data in A and data out B. And this is our device under test, which is the top level VHDL code, which I just showed you. And here is our clock process. It's a 50 megahertz clock with a 20 nanoseconds period. That's clock A. Clock B is a 33.3 megahertz signal clock, with a 30 nanosecond period. That's clock B process. And the data or stimulus is in this process here. And as you can see, it's an incrementing logic vector, so it'll start off at 0 and go all the way up to 20. And that's the data going into the data input A. And so that drives data input A, and that'll go through the two flip-flop banks and come out on data output B. Okay, so the next step is to run the synthesis. Okay, our synthesis is done. It's been synthesized. And let's open up the constraints wizard. The constraints wizard is the closest, or the quickest way to find out in your design flow. It does show up later in your implementation run. It'll flag some errors or some warnings. But if you want to see it quicker rather than later, you can look at your timing constraints wizard. And since all my constraints are already set up, I can just hit next a whole lot of times until I get to the right screen. There it is, the asynchronous clock domain crossing screen in the timing constraints wizard. So this tells you that you have a source clock, clock A, destination clock B, 8 endpoints, and 8 unsafe and unknown issues. So there you go. That tells you that you're crossing the clock domain in an unsafe manner. And if you want to fix that, I can fix that real quickly here. I already have the code for it. We can implement the two flip-flop synchronizer we discussed earlier. I can comment out the single flip-flop, and I can put in the two flip-flop banks, which makes a synchronizer. See, we have data cross. Data cross is coming from the output of the first flip-flops which are clocked by clock A, the clock domain A, and then you have clock domain B, and the data cross from the output of clock domain A comes into clock domain B, and then I put it through a bank of flip-flops, and that becomes data cross 1 on the output, and then I put that output into the input of the second bank of flip-flops, and it becomes data output B on the output of that second bank of flip-flops. So there's a synchronizer, and it's 16 total flip-flops because there's 8 bits. The signal has 8 bits. So let's go ahead and save that, and then we'll run the synthesis, and we'll synthesize the design. Okay, the design is synthesized. Now we'll open up Constraints Wizard. Okay, next. Gotta find the screen that's important to us. There it is. Okay, so now we've had a change here. So we have clock A is the source, clock B is the destination, 8 endpoints, but now we have 8 safe issues. The issues has been resolved because we put in synchronizers. And these are the new constraints that we have that will be added to our constraints file. So Vivado knows now to ignore the clock domain crossing, and that the clock domain crossing has been handled safely. So we got those, and there's basically 8 constraints plus another constraint, which is set clock groups dash asynchronous dash group get clocks clock A, get clocks clock B. So those are the constraints that it will generate. Finish, and now we successfully handled the clock domain crossing, and the data will pass safely from clock domain A to clock domain B. Anyway, I hope you enjoyed this video, and if you liked it, please like and subscribe, and stay safe, and I'll see you in the next video.